Hello, so we'll continue with chapter 20. Chapter 20 will be on 3D kinematics of a rigid body. So it will be similar if you want to chapter 16, but in chapter 16 we considered 2D cases. Now we'll consider the most general 3D motion. So in this chapter, we'll study first rotation about a fixed point, then the time derivative of a vector measured from either a fixed or translating rotating system. We'll see also what are the equations to deal with in general plane motion and the relative motion analysis using translating and rotating axis. So it's exactly, if you want, nearly the same outline of chapter 16, but now in 3D motion. So first, in general, before we just studied rotation or general plane motion in 2 dimensions. So the axis of rotation was always perpendicular to the plane of motion. And the alpha and the omega were both along z. So if motion is in xy, omega and alpha, angular velocity vector and the angular acceleration vector, were along z, positive k or minus k, depending on the direction, if clockwise or counterclockwise. What is new here is that the axis of rotation can change in direction in 3D motion. So omega can have components along I, j, k, and also alpha can have component along I, j, k. And we'll see together that omega and alpha can be of different directions. Okay, not like 2D motion. So from here, to start with, we need to define how to calculate the total angular velocity of a system in 3D. So we'll introduce the Euler's theorem. This theorem states that two component rotations about different axes passing through a point are equivalent to a single resultant rotation about an axis passing through the same point. This means that if you rotate about this axis and you have a certain elementary rotation about it, and then you rotate about another axis, you can say that you can find the omega total as being an angle, a rotation about an axis passing by the same point. Okay, so sometimes you can have rotation can be decomposed into several directions. Yani a resultant omega can be divided into rotation about axis 1 and rotation about axis 2. But when we sum the two rotations, okay, we see that the 3 omega vectors will pass through the same point. And if more than 2 rotations are applied, they can be combined into pairs, and each pair can be further reduced to combine into 1 rotation. So the idea is I can divide rotation into different directions, but in case I have rotations about 2 axes passing by 1 point, the resultant should also pass by the same point. And we'll discuss now what we mean by finite rotations and what is the difference between, if I take finite rotation and if I take non-finite rotation. So let us consider the following system, okay? And if I want to apply, if you want 2 finite rotations, let us say first I rotate about Z an angle of 90 degrees. And then I rotate about Y an angle of 90 degrees. I will see the final position of my face. And here I have a face that was labeled, okay? And the final position of this face is here. Why I am doing this? Because I want you to see that in finite rotations, the order is very important. And if I rotate first about Z in 90 degrees, then I rotate about Y 90 degrees, it's not equivalent to rotate first about Y then about Z. So you can see this in the next slide. If I do the opposite, and I rotate first about Y, then about Z, I will have here, my face will be at this level, which is different from the previous case. So this will show you that the order of rotation is very important when I talk about finite rotation. Okay? While if I take elementary rotations, يعني if I say I want to rotate a small, very small angle, infinitesimal angle theta 1, d theta 1, then rotate d theta 2. When I do analysis in infinitesimal rotations, I can say that d theta 1 plus d theta 2 is equal to d theta 2 plus d theta 1. That's why from this analysis, I can deduce that whenever I deal with rotation in infinitesimal way, I can consider that this infinitesimal rotation can be treated as a vector. So I can say d theta 1 plus d theta 2 is equal to d theta 2 plus d theta 1. Because you know that for vectors, if I add a plus b is equivalent to do b plus a. While for finite rotation, I cannot classify them as vectors. Okay, that's why we'll do the derivatives in infinitesimal rotations. So when defining the 3D angular motions, only
دكتور
yes, yes.
قبل هيداك الثيورم قلت شيء قبله لما احنا فتنا بس مخرين دقيقة قلت شيء قبل هيداك الثيورم اللي
ما
قبله
كان في كهرباء.
Okay, we just said that if you want, if you have rotation about, if you are rotating about an axis with angular velocity omega 1, and at the same time you are rotating about another axis with angular velocity omega 2, then your resultant omega will be the summation of these two. And the resultant axis of rotation will pass by the same point. And if omega 1, omega 2 are passing by this point, the resultant will also pass by the same point. This is the idea that we discussed before. And then we discussed that finite rotations are different. Theta 1 plus theta 2 is different than theta 2 plus theta 1 because you don't reach the same location. While for infinitesimal rotations, it doesn't matter if you rotate d theta 1 before d theta 2 or not. The summation will be the same. And you will end up with the same final position. Okay?
اوكي دي ميرسي.
Welcome. So now, since as we said, so you can see here this slide is summarizing what we said. So if you have elementary rotation in direction 1 plus elementary rotation in direction 2, you can sum these two rotation vectors to get d theta total, and then you can say that omega resultant, which is omega 1 plus omega 2, is equal to d theta by dt, and this vector should pass by, the three vectors will pass by the same point because omega 1, omega 2 were passing by O, so omega total will also pass by O. And we know already, okay, that if we consider elementary displacement angle d theta 1, d theta 2, this corresponds to if you want curvilinear motion, and if you want to determine the displacement in curvilinear coordinates ds, okay, we can say that point P will move along path d theta 1 vectorial r plus d theta 2 vectorial r. So this is ds1 and this is ds2. Okay. So for two successive rotations occurred in order, d theta 2 plus d theta 1, the resultant displacement will be equal to d theta 2 vectorial r plus d theta 1 vectorial r. And then we can deduce that when a body is subjected to an angular rotation d theta, we can define the angular velocity of the body as omega equals 2 d theta by dt. And the line specifying the direction of omega, which is collinear with d theta, is the instantaneous axis of rotation. Now, since, as we mentioned, d theta is a vector quantity, also omega will be a vector quantity, and it follows from vector addition that if the body is subjected to two component angular motions, and the resultant angular velocity will be, so if you have, if your rotation can be divided into rotation about different axes, your angular velocity also omega total will be the summation of angular velocity about axis 1 plus angular velocity about axis 2. From here also we can define angular acceleration. The angular acceleration by definition, alpha vector is derivative of omega vector with respect to time. So alpha is omega dot. And as the direction of the instantaneous axis of rotation will change in space, okay, this means that omega is not variable only in magnitude, but also in direction. That's why alpha vector, which is the derivative of omega with respect to time, okay, will have a different direction from omega. And in general, in 2D, alpha and omega are collinear because omega is only changing in magnitude, not in direction. But in 3D motion, since alpha vector represents a variation of omega vector, and omega vector is varying with direction and magnitude, we'll see that alpha vector will be decomposed into two parts. One part due to the change in magnitude of omega, and one part due to the change of direction of omega, as we'll see in next slides. So that's why in 3D motion, omega and alpha are not collinear anymore, okay? You have alpha and omega collinear in case you have 2D motion. In 3D motion, alpha and omega are not collinear because omega is just, whenever omega will change in direction, alpha and omega will not be collinear. If omega is only changing in magnitude, not in direction, then alpha and omega will be collinear. And now we know that from previous analysis in chapter 16, we know that the velocity of rotation of a point, so if a point is doing rotation about fixed axis, the expression of velocity is omega vectorial r. Okay, and if you remember, when we studied acceleration in rotation, we said that acceleration vector can be divided into two components: tangential, so a alpha vectorial r is the tangential component of rotation, and the normal component a normal is omega vectorial r. In 2D, if you remember, in chapter 16, we said that in 2D motion, because alpha and omega are always collinear, this term, omega vectorial r, which represent a normal, can be replaced by minus omega square r. This is only valid in 2D, because alpha and omega are collinear. So when alpha and omega are not collinear, to calculate an, you should do omega vectorial r. And please pay attention for the order. You evaluate omega vectorial r first, then you do omega vectorial, the result you obtained. After evaluating this vector, so you should respect the brackets. You evaluate omega vectorial r, then you place it here, and you do omega vectorial, the result. Okay. Now, as we were,
دكتور
yes, yes,
بس سؤال سريع لأنه ما كنت كتير مركز. الأوميجا فيكتوريال R هي الفيتاس تانجنسيال.
yes, it's the velocity. أصلا ما في فيتاس تانجنسيال وفيتاس نورمال. يعني in UT you
ما في.
only have V along UT. Yes, it's the velocity along UT because UT is the unit vector of V.
أوكي.
Okay, while A in
دكتور
UTUN frame, the acceleration is decomposed into tangential component and normal component. The tangential component is alpha vectorial R, and the normal component is omega vectorial R.
أوكي.
Okay?
دكتور انا عندي سؤال
نعم.
شغله صغيره.
Yes.
ليش دغري بلشنا بروتيشن باوت فيكست اكسس؟ ليش ما قطعنا بفكره الترانزليشن؟
Okay. Look here, we are studying 3D motion. In case you have translation, if you want, nothing will change compared to before. Yani, what are the equation of translation? You can have curvilinear translation or rectilinear translation, and we already studied it before in chapter 16. All points will have same velocity. All points will have same acceleration. So nothing specific in 2D or 3D. يعني the same equations will apply. While for rotation,
اوكي
rotation
لما
in
شيء
2D is different than rotation in 3D.
اوكي
Okay?
اوكي
Now, so as we mentioned, we need to know how to calculate the derivative of a vector in 3D if it's changing in direction and in magnitude. So the angular velocity omega is specified in terms of its component angular motion. For example, let us take the following example so you understand better what we are talking about. Consider the following figure. Okay. In the following figure, let me zoom it a little bit. Okay. You have a disk. This disk can rotate about its axis. Okay. And at the same time, the axis of the disk is rotating about Z. Okay, so imagine what we have. You have a disk that can rotate about its axis, but its axis is not fixed. Yeah, the axis of the disk will also do rotation about that axis. So here we can say that if we want to evaluate the total angular velocity of the disk, it's equal to, we can decompose it into two parts. Omega S representing the angular velocity of spinning of the disk about its horizontal y-axis, while omega p represents the rotation of this axis about z. And then we can say that in total, the type of motion is general plane motion, okay? Because the axis of rotation of the disk is not fixed, it's moving. So we can say that we are in the case of general plane motion in 3D. And to find the total angular velocity of the disk, we divide it into two parts. The angular velocity about its own axis plus the angular velocity of the axis about z. Okay, so in this way, we can define here omega as summation of two vectors. Okay, and because omega can be divided into summation of two vectors, whenever we want to calculate alpha, alpha also can be decomposed into two parts, which is the derivative of omega s with respect to time and plus the derivative of omega p with respect to time. Okay, but before being able to determine how is alpha s, how is alpha p, we should develop together how to find the derivative of a vector that is changing in magnitude and in direction. So this is why we will define together XYZ frame that is rotating with the axis of the disk. Okay, and here what is happening if you want? The axis of the disk is rotating about Z. And I will put a frame, I will fix a frame to this rotating axis. I will call this frame small x, small y, small z. And this frame will be characterized by an angular velocity omega. So if you sit on this frame, and if you stand on this frame, and you look at your disk, what is the type of motion of your disk?
Rotation.
Rotation. So here, if you want to simplify the analysis, we'll decompose it into two parts. The fixed rotation, the rotation about fixed axis that we see in frame small x, small y, small z. And if you look from outside, you will see the two effects of rotation of the disk about small x, in small x, small y, small z coordinates, and the rotation of the frame about z axis. So we will consider that omega is the angular velocity of small x, small y, small z about z, okay? And we'll see then if we want to derive any vector in the absolute frame, how to relate it with its derivative in the rotating frame, okay? So let us discuss this now. So what is the idea? The idea is the following. If I define any vector, okay, I can define it in a fixed frame, big X, big Y, big Z, and I can define it also in the rotating frame, in small x, small y, small z, okay? And I want to see what is the expression of this derivative. So since the direction of the component do not change with respect to the moving reference, and if you consider derivative in small x, small y, small z, okay? And first, to take an example in the previous, if I take the previous example as example, okay? If I take any vector, so we said this is the axis of rotation. I can call it, for example, small x. And I have small y, small z attached to the axis of rotation. And if I sit on this frame, for me, the rotation of the disk is a pure rotation. It's a rotation about fixed axis. So for me, if I draw vector omega s, which represents the rotation about axis of the disk, this vector is fixed in direction. It will only change in magnitude, okay? While if I look from outside, it's not the case. This is why I need to relate the derivative of a vector in small x, small y, small z to its derivative in big X, big Y, big Z, okay? So if I consider, let's say, this as this vector, which is the velocity of rotation of the disk about its axis. If I stand on small x, small y, small z, this vector is fixed in direction, but can change in magnitude, okay? That's why if I derive omega s in a frame small x, small y, small z, I will just see the variation in magnitude, but for me, the direction is not changing, okay? So the derivative will be simply a dot x in I plus a dot y in j plus a dot z in k, okay? While if I consider derivatives, okay, in absolute frame, big X, big Y, big Z, then for me, this vector is not only changing in magnitude, but also in direction, because vectors I, j, k are moving, okay, translating or rotating. Whatever is, whenever I have rotation of ijk, then they will change in direction, then their derivatives will not be zero anymore. If they are just translating, if ijk are just translating, then their derivative will remain zero. Only if they are rotating, their derivatives will not be zero. So whenever you have rotation of your frame, you need to consider that the absolute derivative, okay, the derivative of a vector A in absolute frame can be decomposed into two parts, which is, because when you derive this, it's like u times v. What is the derivative of u times v? U prime v plus uv prime. Yani you have a dot xi plus ax I dot, okay, plus ay dot j plus ay g dot, and plus a dot zk plus az k dot. So these three terms are actually represent what? Represent the derivative of vector A as seen in which frame? In the rotating frame. While these three components, which are ax di by dt plus ay dj by dt plus az dk by dt, represent the effect of rotation of the frame x, small y, small z, relative to the absolute frame. Okay, and we can prove that. We know that we can prove that di by dt is omega vectorial I, and dj by dt is omega vectorial j, mathematically, and dk by dt is omega vectorial k. And that's why we can replace this summation, which is ax di by dt plus ay dj by dt plus az dk by dt. We can replace it by omega vectorial A. So what is the general conclusion that we should know from this slide? We should know that for a certain vector, if I derive it in a rotating frame, the derivative is different than its derivative in a fixed frame. Okay, but I can relate the derivative in absolute and in rotating frames using the following relation. So here A dot is the derivative, the absolute derivative, that is considered measured in big X, big Y, big Z. This component represents the derivative in small x, small y, small z. And this one represents the effect of the rotation of the frame. If I want to apply this result on the disk example, for you to understand better how is the application. So we said we can define first the angular rotation of the disk omega s about its own axis of rotation. Okay. So if I go to the previous figure here. Okay. If I want to derive this term, I want to derive omega s with respect to time and big X, big Y, big Z. Okay. I will say it's equal. I will apply the formula. Okay. So it's equal to the derivative of omega s with respect to time in small x, small y, small z, plus, now my rotating frame, okay, is rotating at which angular velocity? At omega p. And if I take this example, what is omega? Omega is the velocity of rotation of the axis of the cone about z. So it's equal to omega p along k. So it's omega p k, which is big omega. Vectorial vector A. What is my vector A that I am deriving here? In this example, vector A is omega s. So vectorial omega s. Okay. So for example here, what is d omega s by dt in small x, small y, small z? We said that if I am standing on the rotating frame, the disk is only doing rotation about a fixed axis. So omega s will only vary in magnitude, but not in direction. And we said that if omega is not varying in direction, omega and alpha will be collinear. Okay, so if from the point of view of the rotating frame, I have rotation about fixed axis for my disk. So I can say, because I have rotation about fixed axis relative to small x, small y, small z, then when I derive omega s with respect to time in this frame, I will obtain what? I will obtain alpha s, and alpha s will be along the same direction. Okay, because you know, when you have rotation about fixed axis, both alpha and omega will be along the same axis. So this term will actually represent alpha s, and alpha s is along which vector, which direction? It's along y. It's collinear to omega s. So this is alpha sj, while this term will take into consideration the rotation of the frame small x, small y, small z about z. So we should add to this, to alpha sj, we should add omega pk vectorial omega s. So if I replace, so plus omega pk vectorial, as you can see in the figure, omega s is along small y, yani vectorial omega sj. So now if you do k vectorial j, k vectorial j is minus I. Okay, so this component will be minus omega s times omega p along I. Okay, and this means that this is the effect of change in direction, and this is the effect of change in magnitude. So we decompose the derivative to change in magnitude and change in direction. Okay, any question on this?
فيكي بس تقولي سوري دكتور، ممكن
نعم.
سؤال؟
نعم أكيد.
فيكي بس تقولي اي هو ان دايركشن واي هو ان ماجنتيود، لانه عم
أوكي.
بتعلق عنه
اوكي
الشاشه وهيك.
يا انت this term
والسؤال
انت
تاني
بدك
بس
تقول لي، انت
كمان.
جرب قل لي. اوكي try to tell me. نحن هون we derived relative to the rotating frame. In the rotating frame, small x, small y, small z. If you sit on the rotating frame, what is the type of motion that you see for the disk?
rotation.
Okay, rotation about هيدا الاكسس صح؟ Fixed axis.
اوكي.
If you have a fixed axis, you have change in direction?
لا.
يعني أنت when you derive omega with respect to time relative to small x, small y, small z, you don't see the change in direction. You just see the change in magnitude. لأنه for you omega s is always directed along the small y. Okay? That's why this component is representing the change in magnitude. Okay? While this term is representing the change in direction. لأنه it will take in consideration the rotation of this axis about z. Okay?
اوكي، وممكن سؤال بعد؟
نعم.
اذا بس فيك ترجع توضحي فكره انه اي هو الريبير اكس واي زد الصغار واكس واي زد الكبار، شو العلاقه بينهم؟ بس هيك توضيح.
اوكي اكيد. انت petit x, petit y, petit z tourne avec le disque، يعني rotates with the disk. It's fixed to the axis of rotation. يعني إذا بدي أرجع أرسم لك إياها هون. This is the axis of the disk. This is the disk. Okay? Small x, small y, small z is fixed to the disk system. يعني أنا إذا باخد هيدا الأكسس of rotation So this is y, okay, small y, and this is a
Okay.
small z, and this is small x, okay? What is
ولما يبقى
happening now, when the axis will rotate, the y will rotate with it. يعني أنا مش حيبرم الأكسس about that. So when the axis is rotating, y is rotating with it. يعني new position of y إذا الديسك صار هون، السمول y بيصير هون، بيمشي معه. Okay? So small x, small y, small z is attached, if you want, to the axis of the disk. And since this axis is rotating, it will rotate with it. Okay?
Okay, thank you.
بينما big X, big Y, big Z is fixed. Okay? Okay.
دكتور
Now,
اذا تاني بارت من الفورمولا طلع لونج اي، بس انت قلت انه السمول اكس سمول واي سمول زد، يعني هن كانه الواي عم تبرم حوالي الزد، فكيف طلع
صح.
البرودويفيك تبعنا لونج اي طلعت ماينس اي؟
لأنه أنت when you consider, if you want change in acceleration is the derivative of the vector. يعني ما بدها تكون acceleration بتكون وقت كنا بال 2D كانت تكون angular velocity والangular acceleration perpendicular to the plane of motion. يعني أنت why you are expecting it to be along which direction؟ حتكون perpendicular للأكس للتو axis of rotations يلي هن يعني أنت you have two angular velocities, one along k, one along j. When you do, the effect of the change in direction is perpendicular. لأنه أنت بالvectorial product بس تعمل omega vectorial A, which represents the effect of بده يطلع الفector perpendicular to both. صح؟
يس، يعني بده يطلع perpendicular simultaneously على الروتيشن about z وعلى الروتيشن about y،
مظبوط، يعني
فبتطلع
along
x، مشان
I.
هيك I.
Yes, exactly. Okay. Yeah.
دكتور يعني اوميجا بهالشابتر منا بس k or minus k.
مظبوط. هيدا new thing in this chapter. It's not anymore along k or minus k. It can have several components. Okay. And since it can change in direction, so when you find alpha part of it will take into consideration change in magnitude, and another part will take into consideration change in direction. بينما بال 2D